Dear students, today we'll further see the different types of synchronous motors. In the previous class, we have seen cylindrical rotor and salient pole rotor type of synchronous motor, particularly in wound field type of synchronous motor. But we'll see the other three types now. So at the end of this session, we should be able to describe and compare the features of various types of synchronous motor. So to repeat the classification of synchronous motor, which we have seen in the previous class, that there are four types of synchronous motors. Wound field type of synchronous motor. Here, the field winding is provided on the rotor, and hence that field winding is to be connected to external DC supply, and hence such motors are called as excited synchronous motor. The other three motors, permanent magnet synchronous motor, hysteresis synchronous motor, synchronous reluctance motors, are non-excited synchronous motors because in the rotor they don't have rotor field winding. Either permanent magnet or magnetic material can be there. So as discussed previously, the stator has three-phase winding, and if hysteresis and synchronous reluctance motors are there, they are normally used for fractional HP motors, which may use single phase supply at the stator. So we have discussed this. Just to brief, damper windings are used in the synchronous motor. They behave as the squirrel cage of induction motor, so that initially the motor will start as induction motor, and during this, whatever the oscillations are there, they are damped by these damper windings. Once the motor picks up the synchronous speed, the damper winding is not required. Even if the synchronous motor is supplied with variable frequency source, damper winding in such motors can be avoided. So let us first see the permanent magnet synchronous motor. As the name indicates, the permanent magnet synchronous motor has the permanent magnets on the rotor. The rotor has the permanent magnet. The rotor has the permanent magnet. So the permanent magnet is used as a rotor to create magnetic field. So when three-phase winding of the stator is provided with the three-phase supply, it produces a three-phase rotating flux, and that interacts with the flux produced by the permanent magnet. So the torque is produced. The produced torque is very smooth and low noise, mainly used for high-speed applications. That's why permanent magnet synchronous motors finds its applications in high-speed applications. They are very efficient because they don't use brush, very fast, safe, and give high dynamic performance. These are the main advantages of the permanent magnet synchronous motors. Then it can be used for three-phase and also for single phase. That's one advantage. So working principle, when the stator winding is energized, a rotating magnetic field is created. This passes through the air gap and process through the rotor field poles. The rotor field poles are continuously excited, and hence they also have the rotor field flux. And as these motors are not self-starting motors, it is necessary to provide a variable frequency power supply. So based on how the permanent magnets are mounted on the rotor, we can have two types of synchronous motors. One is surface mounted permanent magnet synchronous motor, buried PMSM or interior PMSM. In case of surface mounted, they are also called as a projecting type, and buried type are also called as inset type. So in case of surface mounted permanent magnet, we can see here, this is the stator core. This is the stator core. Now the rotor core is here, On the outer surface of the rotor, the permanent magnets are placed alternately with the north and south. The air gap between them is very small, and hence we can say that even though it is a surface mounted, it is almost like a cylindrical type synchronous motor. So therefore, the power and torque equations which we have considered for cylindrical type wound field type synchronous motor, the same equations are hold good here. That is, mechanical power developed is equal to 3V into Vf by Xs into sine delta, and T is Tm by omega ms, and hence T torque developed is given by 3 by omega ms into V into Vf by Xs into sine delta. Coming to the second one, buried permanent magnet synchronous motor. Here you can see that the rotor outer surface is circular, and inside you are having the permanent magnets, north, south, like that. As you can see here, the poles are rectangular in shape, and hence there is much air gap or difference in the air gap in between the poles, which results into the reactance of XD and XQ components in the rotor, and hence this interior type of PMS behaves similar to that of salient pole type wound field synchronous motor. So the power equation same can be used now for the torque also, Pm by omega s. So which considers the XDS and XQS components. Permanent magnet synchronous motors are competitive and comparable to BLDC motors, brushless DC motors, because their construction is almost same except the position of rotor and stator are interchanged. PMSM are brushless AC motors, ripples are absent, high efficiency, more efficient, and they are used for industrial applications, tractions, robotics, and produces low noise as compared to the BLDC motors. So the advantages are high efficiency at high speeds, available in small sizes of different packages, maintenance and installation is easy, capable of maintaining full torque, high efficiency and reliability, smooth the torque and dynamic performance. Disadvantages: these motors are very expensive as compared to the induction motors, and if variable speed application is required, then variable frequency source is to be connected. They can be used and are finding wide applications nowadays in air conditioners, refrigerators, compressors, washing machines, uh, automotive electrical power steering, machine tools, even in electric vehicles like this. That is robotics. Coming to the next one, the hysteresis synchronous motor. The two main parts are stator and rotor. Hysteresis synchronous motors are normally used for small power applications, and hence majorly we can find single phase hysteresis motors. So when single phase supply is given to stator, to produce the torque we need another flux, and hence two windings are placed on the stator. One is main winding and another is auxiliary winding, similar to single phase induction motor. The difference here is that both the main winding and auxiliary winding will be connected to supply continuously. Okay, it's not the starting winding, it is the additional winding and is connected continuously. In another type, hysteresis motor, the stator holds the poles of shaded pole type. It's very rarely used, like in mixies like that. Rotor of hysteresis motor, if you see, it is made up of magnetic material which has high hysteresis loss. So the BH curve area should be of very large value so that much hysteresis loss is there. It gives high retentivity of the magnetic flux. If you see the operation of this hysteresis motor, At starting, when the stator is energized both with main and auxiliary winding, a rotating magnetic field is produced. This induces the secondary voltage in the rotor. The secondary voltage is induced in the rotor, and hence eddy currents are also generated. So now there is hysteresis torque produced and also eddy current torque produced. The rotor undergoes under the slip frequency before going into the steady state. Initially, it acts similar to that of induction phenomenon and hence acts as induction motor. And once it picks up the speed, the rotor gets locked with the stator flux. So in the running condition, at this condition of synchronism, the relative motion between stator and the rotor field vanishes, and therefore no induction phenomenon to continue. So with this, what happens? There will be no eddy currents produced. So eddy currents are there only during starting and then reaching synchronism or during transient periods. Thus, the torque due to eddy currents vanishes. Only the hysteresis torque will take over. To have this hysteresis torque of high value, the rotor is made up of magnetic material with high retentivity. So the high retentivity enables continuous magnetic locking between stator and rotor, and motor runs at synchronous speed. Induced magnetic pole axis always follows the rotating magnetic field of stator without any lag. Normally, the rotor has locking with the stator flux and does not lag. But if the load torque is of large value, then the rotor pole axis lags behind. It lags behind but runs with a synchronous speed. So this lagging angle can be called as delta H. This reaches a maximum value as the load torque is increased. If load torque is still further increased, it may lose synchronism. So we have to take care that this delta H does not exceeds delta max. The torque produced, for all the range of speed is constant. So the starting torque, running torque, and maximum torque all are same, and hence it is equal to the hysteresis torque produced. So advantages with the hysteresis motor is, as no teeth or no winding is present in the rotor, there are no mechanical vibrations, and hence it offers quiet and noiseless without any vibrations. So they are suitable to accelerate inertia loads. Multi-speed operation can be achieved by employing the gear train. Disadvantages is that they are having low efficiency, low torque, and low power factor, because as the low torque increases, the delta increases. That may result into low power factor. And another one is because of use of magnetic material, it mainly has reactive current absorption and its low power factor is there. This type of motor is available in very small size only, and you can also see through the applications. They are used in sound producing equipment, sound recording equipment, record players, timing devices. So for fractional power applications, such motors are suitable. Next comes synchronous reluctance motors. It is a synchronous electric motor where the torque is due to inequality of permeance, that means magnetic conductivity. So the rotor construction is made such that it has different permeability around its surface. Average, it can give two reactances. These two reactances are called as the direct axis and quadrature axis reactances. So to obtain that one, the rotor can be constructed with the salient poles like this, or with axially laminated rotors. So here the reactance and here the reactance will be different. Here and here will be different. So we can say that we are having XD and XQ values. The laminations can be axial or the laminations can be transverse. So the working principle is that the torque is created when the rotor attempts to establish its most magnetically conductive axis, D axis, with an applied field. So when the stator field, rotating field, uh, crosses the air gap and uh, touches the rotor, the magnetic conductive axis with an applied is in order to minimize the reluctance. So D axis continues to position in the minimum reluctance position. The amplitude of the torque that is produced is directly proportional to the difference of LD and LQ. So greater is the difference, that is greater is the difference of this value, then greater is the torque created. So advantage is that it is simple and robust rotor construction. Less heat is produced because uh, there is no wires or conductors or no resistive part involved. Then no magnets are there and then less weight, simple in construction, less moment of inertia, and speed control can be obtained if we are having variable frequency source. So disadvantage is that to work it requires a variable frequency drive and low power factor due to the fact that the magnetic flux is generated only by the reactive current. Low power factor is there, and this can be solved by having an additional power correction source or the supply or the converter. So a reluctance motor acts as a salient pole type, and hence the torque equation is similar to that one. But in this case, the VF part is not there, so this term goes to 0, and you have the terms left. So dear students, by now we have seen the different types of synchronous motors, and particularly reluctance, permanent magnet, and hysteresis type of motors. So you should be able to compare the wound field and the reluctance motor, wound field and permanent magnet synchronous motors, and list the applications of various types of synchronous motors. Compare the advantages and disadvantages of different types. So we have come to an end. Go through these questions. These are the possible questions at remember and understand level. So dear students, refer textbook GK Dubey, chapter 7 and these sections. Thank you.